We have an inner conducting sphere. We have an outer conducting shell. Inner sphere has radius A. The inside radius of the shell is B. Outside radius is C. First thing that you're asked to do is to find the electric field in this region of space. To do that, your go-to solution involves Gauss's law. And when you're answering AP questions, remember, you will get probably 1 or 2 points just for stating something fundamental that's probably at the base of solution, but you don't even know where to go next. So there's our 2 points. But we could do better than that. We know that for any given radius r, the electric field is going to be constant, and also the electric field is going to be in the same direction as every single little infinitesimally small area vector. So we can collapse this, get rid of the dot product, and solve for what is the sum of all of those little dA's, and that's 4 pi r squared. And then solve for the electric field, Q, over 4 pi r squared epsilon naught. And that's something that you guys are familiar with. And at this stage of the game, that's probably not a problem for you. Where the problem comes is when we've got to start answering questions about the electrical potential. Now, before doing anything else, if we know that this is positively charged, and this right here, I think in the problem they said it was grounded. Didn't they say it was grounded? Yeah. So all that means is that we've identified this as having an electrical potential of 0. That's all you need to know. Is there still an electrical potential difference between these two? Yeah. And isn't the electrical potential here going to be higher than the electrical potential out here? Well, this is 0. If this is positively charged, it's certainly going to be at a higher electrical potential. The electrical potential difference is going to be negative as you go out. Does that make sense? Always think in terms of potential energy, electrical potential energy. If you're going this way, if you're pushing a positive test charge in closer and closer towards our sphere, what? You're going to have to do some work. And all that work gets stored in the system. So here we go. We're going to answer the question about the electrical potential. And we have our go-to on the equation sheet. Let's see. You are given this. And what we're going to do is rewrite this, and then the next step, it often becomes kind of trivial. Whoops, I forgot the negative sign there. So what we often do is we just say, oh, okay, well, that's easy. Just write V. So the integral, you've got the differential here, but it's not trivial. I want to stop for a moment and remind you the limits of integration. What this does is it reminds us that when you evaluate this integral, the electrical potential difference is going to look like this. And if you don't mind, I'm just going to put our how we define the electric field for this particular geometry. So I'll substitute this into here. This, by the way, is constant, 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 constant. So I'm going to bring that out front. And now we can do our integration. And I'm going to continue to write our electrical potential difference that way. This, of course, becomes Q over 4 pi epsilon naught over R. And this is our initial, our final, and now, this is where we end up. And what this does is it takes care of all of our little problems involving that negative sign. And, well, wait, what if you start here and go here? What if this is initial and that's final? Well, wait, what's that going to say if we compare it to what happens if you start here and go in? Well, the good news is that if we remind ourselves that this right here is the electrical potential where we end up, and it corresponds to that position. So remember, electrical potential, it happens at a position. And so let's do this. We're going to do this in two different directions. The first time, let me see if I can fit all of this in this space here. The first time, let's go from B to C. I'm sorry. Let's go from A to B. So we're going to go from here out to here. So what's that going to look like? We're going to end up at B. And if you don't mind, the 1/4 pi epsilon naught, I'm just going to write down as K. And our final minus initial. All right. We know this. We have identified this as 0. We've said that it's grounded. Therefore, we're left with negative, whatever the electrical potential at A is equal to, or Coulomb's constant times the amount of charge we have, 1/V minus 1/A, except for one thing. B is bigger than A. If B is bigger than A, what happens here? This is smaller than this, and therefore, what is this term going to end up being? Negative. And so we end up with a way of describing our electrical potential at A. It's going to be positive. So let me I want to emphasize this. I'm just going to tell you this electrical potential at A will be positive. All right? That's fine. Let's do this again, except this time we're going to go from B in towards A. We're going to start here and head in towards A. So we take, where do we end up? That's A, minus our electrical potential where we start. Over A, minus 1/B. And we have defined that as 0. And once again, we end up with what we would expect. This right here, A is smaller than B. A, that distance here, is smaller than B. So this ends up being positive. And sure enough, in both instances, we end up with the exact same answer. We know that the electrical potential at A has got to be positive. In fact, it's going to be the biggest of anywhere you're going to find it. And then the same thing if you go in the opposite direction. So does that kind of clear up the issue with the negative sign? The key, as I started thinking about this, is not making this trivial. Making sure that you understand that there's a potential difference right here. Maybe we'll go all the way down to where it's been solved. There's an electrical potential difference right here, and it correlates with how we define our positions. So if that's our final position, there's a corresponding final potential. Our initial potential is going to correspond to our initial position. And then the last part of this question involved finding the capacitance. Well, by that point, the question is always, anytime you're asked a question about capacitance, what do you want to think about? Yeah, how does it function? So Q over V. We're told what Q is. We just solved for the electrical potential. And so it's a pretty easy question about the capacitance. Although, wait, now I'm remembering, there was something different about this problem, wasn't there? Is this the one where you added? Oh, that's right. So let's go back to that. So in this problem, what they did was they took the capacitor and filled it with oil. This also might take a little bit of explaining. What you effectively have here are now two capacitors, and they're in parallel. How do you know that they're in parallel? Because this right here, okay, we could cut our capacitor in half, and these two capacitors are in parallel. This is at the same potential as this. This top half here is at the same potential here, and we know that when you have two capacitors that are hooked up in parallel, you simply add them. So if we're trying to find the new equivalent capacitance, we simply have to add these together. So the top one is simply going to be our original capacitance divided by 2, and then the bottom one is also our original capacitance divided by 2, but it has that dielectric oil which has a constant of 4 in there. And so our equivalent capacitance ends up being 5/2 of what the original was, or 2.5 C. So